On behalf of me crew, I'd like to tell ye about Armada, a language and tool allowing developers to write and prove correct high-performance concurrent code. Armada has four main goals, the primary one of which is to give developers the flexibility they need to write the high-performance code they're going for. So we don't want to dictate a particular code structure to enable writing proofs. We don't want to demand that they use a particular synchronization mechanism, or even that they use any synchronization mechanism at all. They might be writing a lock-free data structure library, or a piece of code like this one, a solver for the traveling salesman problem. This is searching through a space of solutions looking for the best one, the one with the shortest path. So in this snippet of code, you'll notice there's this benign race where it acts as the global variable best guess without holding any lock. But this is benign. It is safe to do so because even if it sees a stale value, it's still going to acquire the mutex and read it under the control of that mutex. Our next goal is realism. We're going to run these programs on real machines, so we need to model those machines' behavior. In particular, we want to model their weakly consistent memory. So we use the x86 TSO, or total store order, weak memory consistency model. Third, we want to reduce the burden on the developer in writing proofs. So we're going to do that with automation. We have a tool that automatically generates most of the proof using only a modicum of developer guidance. And finally, of course, we want soundness. We want our proofs of correctness to be themselves correct. I'll now overview the workflow of Armada, describe how a developer uses it. They start by writing an implementation, which is meant to be compiled and executed, and a specification, which is meant to be read and evaluated by a human, to decide whether the implementation should be considered correct if it conforms to that specification. Now, the Armada language has a number of features that are useful in an implementation to get high performance, like pointers and structures, and the ability to create numerous threads. The specification language is richer. We can put things in the specification language that we don't know how to compile or execute, because the specification is not meant to be compiled, it is only meant to be read. So, for instance, we can have unbounded size integers and infinite sets. We can't implement this on x86, but we don't care. We can have atomic blocks, blocks that cannot be interrupted in the middle by other threads. We can have TSO bypassing assignments, assignments that directly update the memory as viewed by other cores immediately. This is essentially sequentially consistent memory assignment, which isn't found on x86, but again, we don't care. The specification is never going to be compiled, only read. So once you have the implementation and the specification, the final goal is to prove refinement between them. That is, to prove that all behaviors of the implementation, as seen by the external world, are also behaviors of the specification, and thus can be considered correct. So proving refinement from the implementation to the specification is a pretty big leap to make, especially given that we're giving developers the flexibility to write the implementation however they like. So we require the developer to bridge the gap for us between the implementation and the specification, and this is where the concept of refinement levels comes in. So the implementation we call level 0. Then the developer writes level 1, a slightly more abstract version of the program. And then level 2, more abstract, and level 3, even more abstract, and so on, until they reach the specification. Now, at this point, it's Armada's job to generate a proof of refinement, but it can do that level by level, generating for each pair of levels a proof of refinement between those pairs. Now notice that this automatic proof generation is only semi-automatic. We still need the developer to provide guidance in the form of what the levels are, and also in other forms like providing invariants. An interesting thing to note is that only level 0, the implementation needs to be compiled. So we're free to use in level 1 and above, all of the specification features like unbounded size integers and atomic blocks, because those levels are not going to be compiled. They're only useful for proof purposes. So every pair of levels represents a transformation of one program to a more abstract version of it. And if that is a big gap, well, a wizard like me could effect that transformation by writing a manual and complex proof, but that would be a lot of toil and trouble. Since we want to generate these proofs automatically, we want the gap to be narrower. We want these transformations to be simple. So, for example, we might use weakening, where one statement is replaced by one that has a superset of its behaviors. In this example, coming from the traveling salesman example, we're replacing the comparison to the global best guess with the choice of an arbitrary Boolean. Now this is useful because the program on the right is easier to reason about. It no longer has the benign race. But it is just as correct because, as I argued before, it doesn't matter what the comparison winds up as. The program is still correct. The programmer expresses this to our automatic proof generator by supplying a recipe. They say these two levels differ only by the transformation of non-deterministic weakening. And weakening is not the only example of transformations that we allow, where we replace one statement with a superset of their behaviors. We also allow variable introduction, where we introduce a new variable, a ghost variable, to shadow some concrete state, or variable hiding, where we get rid of an old concrete variable that we no longer need because we have shadowed it with a ghost variable. We support more complex transformations like TSO elimination, where we replace an assignment to a variable using TSO semantics with a sequentially consistent TSO bypassing instruction. Or more complex yet, reduction allows us to replace a block of statements with an atomic block of statements that can't be interrupted using Lipton's reduction approach. And rely guarantee, that allows us to use rely guarantee reasoning to introduce assume statements that are enabling conditions on subsequent statements, effectively embedding invariance in the program that can be obtained by using a concurrent variant of Hoare logic. And we can have more in the future. As more and more papers are published at PLDI describing more ways to reason about concurrent programs, we can incorporate those into the Armada framework. In other words, our proof generator is extensible. But why is that extensibility sound? Well, the proof generator takes input from the developer and produces proofs, but we don't trust those proofs. We require them to be passed to an automated theorem prover, a verifier that will tell us whether the proofs are correct or incorrect. We only accept them if the verifier says they're good. So that means that our proof generator is not trusted, and so our TCB is small. For instance, if our rely guarantee proof generator, which is a fairly complex piece of code, were incorrect, well, then we would produce bogus proofs and we wouldn't accept incorrect results. This is what gives us the freedom to incorporate new techniques without worrying if those techniques are valid or if our implementation of those techniques are correct. Another advantage of checking the proofs with a verifier is that if there's some problem with the proof, it provides feedback to the developer as to what is wrong with their reasoning. Or it shows the developer that nothing is wrong with their reasoning, but just that the proof generation tool was not sophisticated enough to figure out the reason why the program was correct. So for instance, the developer might be trying to weaken the expression cosine squared plus sine squared equals 1. And no proof generator is going to be able to have so many cases that it could reason about this, but Armada provides the ability to do proof customization. The developer can specify in their recipe to stick a little bit of extra custom proof into the generated proof, and thereby make up for shortcomings in the necessarily general proof generator. When compiling an Armada program, we have to do so in a way that produces an executable that is consistent with the assumptions that we're making about Armada semantics. Unfortunately, this is possible because Armada is close enough to C that we can directly translate into dialects of C, including C-Lite TSO, which is supported by CompCert TSO, a compiler that assumes, and provides x86 TSO semantics. We could also compile with GCC, but that we should only do so to just get a sense of what performance could be with a better compiler. We don't expect soundness when compiling with GCC because GCC does not understand or provide TSO semantics and might perform transformations and optimizations that are not consistent with the assumptions that we're making. And now I'll share with you some evaluation results demonstrating Armada's utility. Our first example is a barrier program, and this is a program that doesn't lend itself to an ownership-based proof. But Armada can still prove properties of it because we don't enforce any particular synchronization mechanism. So we give developers the flexibility to build programs like this. Our pointer-based example demonstrates that as part of automatic proof generation, we can do automatic alias analysis. A more complex example is the Mellor-Crummian-Scott lock, which is a high-performance piece of complex synchronization code. This was proved correct by the folks at Certicos, and we show that we can do that with a lot less, about 90% less, input from the developer. And finally, we have an end-to-end example, a lock-free queue from the liblfds library. This is a demonstration that Armada can support complex, lock-free data structure libraries without compromising on performance. And let me show you some performance from that. So on the y-axis is millions of operations per second using a benchmark built into the library. And on the left is the built-in queue. So the first thing we did was port it to be a little bit simpler, to not use a bit mask operation and instead to use a modular operation. This isn't a fundamental limitation of Armada. We just wanted to focus on the key contributions of Armada, which were about concurrency and weak memory models. So we find that when we port this to Armada and compile with the same compiler, we get virtually the same performance, which isn't surprising because Armada is very much like C. Somewhat surprising is that when we compile with CompSer TSO, which is sound, we still get very high performance. And so we can see that we can support high-performance lock-free data structures with Armada. Armada is not done. So let me gaze into my crystal ball and see the future work that lies ahead. Well, for one thing, while we have striven to keep the trusted computing base of Armada small, there is room to make it even smaller. Second, while we support the weakly consistent memory model found on x86 processors, other processors like ARM and Power we do not currently support, but would like to. They have different memory models. Third, levels may remind you superficially of layers, as found in CSpec and Certicos. Layers are a powerful technique for achieving modularity, reasoning about one component of your code separately from the other components of your code. However, in Armada, we require all of the components of your code to be together in level 0. Now, we don't think that levels are incompatible with layers, so we would like to add layers and the resulting modularity to Armada. Finally, Armada currently only reasons about finite behaviors. Infinite states, sure, but only finite length behaviors. So we can only prove safety properties, not liveness properties. That said, Armada is under current active development, so please watch our GitHub repo and perhaps even contribute to it. So, in conclusion, Armada's methodology allows developers to write and prove correct high-performance concurrent code, however they want to achieve that high performance. The developer makes a proof by providing us guidance in the form of a sequence of successive abstractions of their program leading to the specification, and we automatically generate a proof that is checked by an automated theorem prover. This tool for generating proofs is extensible and allows a variety of program transformations to be used by the developer. The proofs that are generated, if they fail, give guidance to the developers to how to fix the proof or how they can customize the proof to make it go through. Thank you for your interest. If you want to learn more about Armada, you can read our paper and you can go to our GitHub repo. Thank you.